One of the best parts of my job is when a student who's been trying to understand something and hasn't quite got it asks me a question. And sometimes I've never heard these questions before, so it's a really good opportunity for me to get inside the mind of a student and understand what they might be struggling with. And this happened quite recently in the context of the decay constant for radiation. Now, we teach the decay constant for radiation by saying it's a constant of proportionality between the activity of a source and the number of undecayed nuclei in that source. Undecayed, radioactive, unstable nuclei. Another way of thinking about it, it is the probability of decay per unit time. Let's take the unit time as per second in the rest of this video. So we can say that this is the probability of decay per second for a nucleus. And if we multiply that by the number of nuclei we have, we get the activity, how many nuclei decay per second. Or another way of thinking about it is on average the proportion, the fraction of nuclei that decay per second. It amounts to the same thing. And that's what we teach, and the students will say, okay, I get that. And then we might say something like, well, let's take some dice and let's roll some dice. We might say, count how many dice you start with, and then every roll we remove all the number sixes, for example. There's a lot of sixes in there. Vegas is calling. Right, there we go. That's probably all the sixes. Maybe I should leave a six there just so someone comments. No, I'll leave that. Then you count how many dice are there, write it down, then you roll them all again, put them to one side, roll them all again. That's where it goes wrong. And remove all the sixes again. And you can repeat that process again and again and again and again, and count how many dice you've got left, and keep going and keep going and keep going. And then you plot a graph, and from that graph, you can measure the half-life. And students are generally quite happy with that. They understand that. But this student I'm talking about, the problem they had, this camera keeps going out of focus. It's not very good, is it? The problem they had was that they didn't understand. I'll hold my hand there so it stays in focus. The problem they had, they didn't understand what happens when you say the probability of decay is 50%. So let's imagine with these dice, I'm rolling them every second. Every second, I roll every dice, collect them all up. Then the next second, I roll every dice, collect up. Next second, I roll every dice. But I remove the dice that are, let's say, even, and just keep the odd dice. Now, if I do that, this is what the students said I'm going to get. They said I'm going to get a graph where we have 100% of all my dice at the start. After the first roll, on average, I will have 50% of the dice. On the next roll, on average, I will have 25% of the dice, and we'll be going down like this. I'm just going to do it very roughly, going down like this, halving each roll. Just like that. And if I were very talented at drawing graphs, and I'm not, then we might be able to draw a line of best fit that goes through all of these. Oh, how's it looking? Missed. Not great, not perfect, but you get the idea. Just missed there. Annoyed with myself. So that is what the student was saying. And then, of course, you could just say, well, it halves after one roll. If we're rolling once per second, then the half-life is 1 second. The half-life is one roll. Well, that makes sense. If I'm removing all the dice that are even, I'm removing half the dice each roll, then the half-life is one roll. But that didn't seem to check out with the mathematics. So they were confused by this. And this is what they asked me. They said, well, look, you've told me that the relationship between the half-life and the decay constant is natural log of 2 divided by the decay constant. When I chuck that into my calculator, I do not get the value of a half. Obviously, I don't get the value of a half. Pause so I can go get my calculator. There we go. So here's a calculator. Let's try and get it so there's no glare on the screen. Let's do the calculation then. Natural log of 2, and we are going to divide that by the decay constant, which we said was half. The probability of decay per roll was half. Oh, that's interesting. A half-life was 1.36, so 1.39 rolls. That seems to disagree with what that student's intuition said, which is it should be half-life of one roll. And if we roll once per second, half-life of 1 second. So what's going on? And I said, well, okay, let's just do a quick derivation. And I do this derivation in lessons anyway, but I said, let's just do a quick derivation. I'll leave that there because maybe it'll help the camera focus. And it goes like this. We're starting with this, and we're saying that the activity is the rate of change of the number of, in this case, dies. And so we could say the activity is equal to this divided by this. Change in the number of dies divided by the time interval, r. But it's a decay. We're reducing that number. So final subtract initial. Let's go with a minus there. So the activity remains as a positive number, even though this is a negative number. So that's why we shove a little minus in there. There's fewer dice at the end than there are at the start, so final number of dice minus initial number of dice is going to be a negative number, but we want an activity to be positive. So okay, let's plug that into here, and we can say that dn over dt is equal to minus lambda n. Okay, fine so far. I've just moved the minus to the other side, times both sides by -1. And then what do? Well, I rearrange this to gather all the like terms. So 1 over n dn is equal to minus lambda dt. Then what do? I integrate. I sum up all those small changes here and here. Well, minus lambda, that is just a constant, so that comes outside the integration. Summing up all the t's is going to be, all the little intervals of t is going to be t plus some constant of integration. The other side, the natural log of n plus the constant of integration is the integral of 1 over n dn. And I've done a proof of that in my video about, or one of my videos in my video series about calculus for physicists. Yes, there's a constant of integration, but I'm just going to absorb that into this constant. So there we go. Then what do? Well, e to the power of this is equal to e to the power of this. E to the power of that is just n. E to the power of minus lambda t plus c. And using laws of logs, we can split that into e to the minus lambda t multiplied by e to the c. What is e to the c? Well, when t is equal to 0, this term is equal to 1, and so n would equal EC when t equals 0. So let's call EC n0, and just because it's a constant, let's move it to the left. So that's just how we're writing things. That's our equation. So far, so good. Now we want to care about half-life. So we're saying that when n over n0 is 1/2, so just dividing through by n0, that's going to be equal to e to the minus lambda t subscript a half. That's the half-life. So half that. Let's take the natural log of this and the natural log of this. Natural log of a half, I'll just write it as natural log of a half for now. We'll split it in a bit. E to the power of that, natural log of e to the power, so they're inverse functions. You end up with that. What's natural log of a half? That's going to be the natural log of 1, subtract the natural log of 2, is minus lambda t subscript a half. Natural log of 1 is just 0, has to be. What do you raise anything to the power of to get 1? 0. So that's going to be minus natural log of 2 equals minus that, multiplied through by -1, and you end up with natural log of 2 is equal to lambda t subscript a half. Rearrange it. T subscript a half is equal to natural log of 2 divided by lambda. Well, that is exactly what we were using before. That is what we were using. And that is what predicted that we had a half-life more than 1, a half-life of about 1.39. And the student was uncomfortable with this because their intuition told them that the half-life should be 1. Can you spot the mistake they made? Well, let's see if I can make it a little bit clearer. You can see I've got this green line. The data points the student had, let's say they were correct. At 0 rolls, there were 100% of the dice. At 1 roll, there was 50% of the dice, and so on and so on. These data points, let's say they're correct. But it is not correct to say at half a roll, there was round about 70-something, 74% of the dice. That's not correct. No, because we had a discrete series of rolls. We either rolled or we didn't. So the number of dice that we had between the 0th and the first roll was 100%. Then we rolled, removing half the dice, and then we had 50% of the dice. And then we rolled, removing half the dice that had left, and then we had 25%. Let's try and line this up properly, make an effort. And then we rolled, and then we had 12.5%, whatever that's supposed to be, about 12.5%, not quite round up there. And then we rolled, and so on, and so on, and so on. And so you can see that the number of dice we've got is always a little bit more. Apart from at the actual instant of the roll, we always actually have more dice than if we were using a continuous series we would have. So this is what we call a discrete pattern rather than a continuous pattern. The green line is continuous. So the green line is showing what happens with nuclei of atoms, and the red one is discrete. That's showing what happens with dice rolls, because you can't actually have half a roll of a dice. Time is continuous, but number of rolls wasn't. And now you can start to see what's going on, you see. The half-life is not actually 1. If we try to take an average of all these dice, you can see it's always a bit higher, the number of dice, than the green line can't get the words out, than the green line should suggest. So if we somehow do some sort of clever averaging through this, you'll see that the half-life now is going to be a bit higher in terms of number of rolls. In fact, it's going to be about 1.39 rolls. Well, of course, you can't get 1.39 rolls because it's a discrete series, hence why they got confused. Well, I hope that's helped. I hope that's helped clear up and solve this student's little conundrum. It's just getting mixed up between continuous physics. We model some things using continuous mathematics, and in this case, the reality, which is a discrete situation. Now, sometimes we actually do it the other way around. Consider Maxwell's equations and electromagnetic propagation. Maxwell's equations are continuous equations. Now, just pick two of them. We've got curl of E is minus del B by del T, and you've got curl of B is equal to, let's keep it simple, mu 0, epsilon 0, del E by del T. Okay, that's a very simple case where we don't have any free charge carriers. So the current density is going to be 0. So it's a very simple case. Now, where we've got this, you can see that these, what I call dels, partial derivatives, sometimes people call these dels, but these are the letter nabla, so I call these dels. So these often just get called d's, but I'm going to call them dels. So del b by del t is a partial derivative. Del e by del t is a partial derivative. It's the same physics. It's a continuous physics. That can be quite difficult to model. If you're trying to predict the propagation of electromagnetic waves or a pulse of electric field or anything like that, that can be quite difficult. So what we often do is a technique called finite difference time domain. Finite difference means we split this and we take dt as being a discrete interval of time rather than an infinitesimal interval of time, so we get a continuous change. We take it to be a delta t instead of a del t. When we do that, we can model pretty successfully in lots of situations the propagation of electromagnetic waves. But under some circumstances, for example, where you've chosen your delta x or your delta y, delta z, your spatial interval, rather than being continuous, it's going to be discrete. When you do that, if your wavelength of your electromagnetic radiation is smaller than, let's say, 10 of those, it's approximate, you're going to start getting artifacts in the simulation that aren't there in reality. You don't see these artifacts with electromagnetic radiation, but the simulation predicts you're going to get them. The regions of higher intensity, regions of lower intensity. Well, what's going on there? They're not really there. They're artifacts of the simulation. They're artifacts of the fact that we are trying to model a continuous physics using discrete mathematics. And this is sort of the reverse of what we're doing here with the dice roll, where we're modeling a discrete mathematics with discrete physics, with continuous mathematics. It works pretty well in some circumstances, but it's not hard to find circumstances where it just doesn't work. Now, if I have enough dice and I have a small enough time interval, actually it starts to look more and more like this red line approaches the green line. And in the case of nuclei, what have we got? Well, we have a discrete number of nuclei. It's not a continuum. Time may be a continuum, maybe it's not. Loop quantum gravity and string theory, loop quantum gravity and string theory disagree. So the jury is out on that. But let's say time is continuous, but the number of these particles is discrete. Well, there's no way with a discrete number of nuclei we can get a smooth curve. You just can't. This equation, where is it? Here, this equation never becomes zero. You never get zero nuclei. Well, that's nonsense. Of course, it must be nonsense. You can't. If I've got one nucleus left, and you say, well, in one half-life, on average, there's going to be half a nucleus left. Oh, that's not going to work. I either get one or I get zero. So, believe it or not, that is discrete physics that we are modeling with continuous mathematics. Now, as long as the time interval is small enough, and we can take the time interval as continuous, and the number of nuclei is sufficiently large, then we can model this discrete situation with continuous mathematics and get really pretty good results. I mean, they're so good, no one argues with them. All right, I've rambled for long enough. Hopefully that's been useful.